some prototype nozzles and radios for the new rocket. So, rocket requirements for Jebediah. It will use liquid nitrous oxide and alcohol as a propellant. The rocket will be 6 inches in diameter, and the rocket will meet all far-out safety requirements. You can find those requirements online on their website. The rocket will not pose a risk to any students or anyone involved. The rocket will fly at the far-out competition. So, as I said earlier, we have a pretty heavy rocket. Most of the weight does come from the propulsion system and the propellant. Not much to say. The RCS is the lightest part of this rocket, and so is the recovery system. So the size comparison of Jebediah compared to one of our members, Jeff. Jeff is 5'7", so we measured him around 3.5 Jeffs. So. And it's going to be really fun to assemble, that's for sure. So the timeline. We just had our PDR in October. CDRs right now. We're hoping in January we could do our tank proof test. Also, in February, we're hoping we could accomplish 2 things: the injector cold flow test and our recovery test flight. In March, we'll have our static test campaign. And if we need to, we'll have our backup recovery flights just in case the flights in February go wrong in any way. In April, all testing data has to be sent to far out, and we have to stop everything we're doing. In June, that's when the competition is. Any questions about timelines, basic things about the club?
You don't have any specific sections on this, but a couple questions are: one, have you looked at transportability? You got a 22-foot long rocket. How would you be transported?
That was my main question at the beginning of the year. Right now, we do have a couple members in the club with truck beds. I believe the longest one we have is a 6 or 7.
No, Doug has when we break it apart, the longest piece will be the tank, at 8 feet long, and we have multiple options for how we could transport that. We could put it on the roof of a car if we need to, but
everything's being designed so we could break it down into the smallest parts that we possibly can. It's just the tank that's going to be the biggest problem.
Okay, that was one question. One missing element of your design team is a systems engineer, because the discipline of systems engineering, you have a bunch of requirements there, and systems engineering should be doing a couple things. One, how the requirements flow down to your various components. Mm-hmm. 2, are you meeting your requirements? Do you have any risks in meeting your requirements? So one part of the discipline that I see missing here is systems engineering.
Yeah.
That's sort of what I do as the chief engineer, but we could probably dedicate more effort to that.
Okay, and as part of the systems engineering, I didn't see any discussion for risk assessment.
So risk assessment, we'll talk about more of that throughout the slides. For every subsection, they'll talk about the risks involved with their section of the rocket, and we also have a slide on safety.
We don't have a specific risk matrix or anything like that on this presentation.
Yeah.
just more overall sense.
Again, it's common for, again, for future and for your professional world.
Mm-hmm.
Normally, systems engineering plays a big part in a CDR.
Yeah.
Just a question for me, to be honest. Do you recommend that if we have like a safety matrix for like AAA launches, like would they like to see that?
Well, more than just the safety matrix. Again,
But yeah.
Yeah, I mean, it's, you have your high-level requirements that's going to flow down to pressure requirements for your tank, volume requirements for the tank. So again, systems is going to help evolve your upper level. Safety is only one element of it.
Yeah, I see. Okay. Yeah, definitely something we're going to have to.
What about an integrated schedule? So you got to work the probability of getting everything you need to have done at the times you need them done. There'll be prerequisites for pretty much every schedule.
Yeah.
Somebody has got to have that. You really have to have somebody who kind of mind melds with the whole schedule as far as what has to happen when and what can't happen when something else happens. That becomes a real challenge to keep that all in check.
Yeah, because I've been kind of in charge of that as like project manager / chief administrator. Honestly, our biggest challenge throughout this year and last year has been shipping delays for every part. Like, oh, we'll have this part created by next week, and everything still hasn't shipped. So that's
As
my
the
biggest concern.
administrator, I would suggest either yourself or finding someone who is familiar with Microsoft Project.
Mhm.
It is a pain to use that program,
Yeah.
but it is a very good program to see where your choke points are.
Yeah.
And how everything flows. If you change one item, you see how it waterfalls into everything else.
Yeah, actually, that's the purpose of our sponsorship with Boltline. I'm actually so glad you brought this up. So it's like Microsoft project, but it's specifically designed for an engineering environment. So it has like workflows that we can share, and you could tie workflows to inventory to track like what parts need to go to what project. I could show more of that at the end if we have time, because I think it's similar to projects. Any other questions? All right, cool. So I'll be handing off the mic to our safety lead, and he'll talk about safety for the rocket. You can click down there.
Just hold it. Alrighty, so. Alrighty. So a bit of an overview before we get started. Our main safety principle is to never put people at physical risk from failure of student-made systems. Commercial systems can also be dangerous. The procedures to ensure proper usage are in place as well. WREC has and creates procedures and safety codes applicable to whatever test is being performed at any given time. Good safety starts from high respect of the power of the system we're working with. So all elements of the rocket have to be considered. And so for factors of safety for the pressure vessels that we use, we test to 1.5 to 2 times maximum expected operating pressure, which depends on each item. And for recovery hardware that we use, we make sure that's rated to twice the theoretical snatch force, which is the maximum force experienced during the parachute deployment. The pressure vessels are designed to burst at 2 times the maximum expected operating pressure, and tested to 1.5 times the MEOP. This is primarily for the tank and the chamber. If GSE takes student manufactured parts, it also gets tested. Pressure vessels are tested with water to avoid explosion in case of burst or incompressible. And humans are never allowed near student-made pressure vessels that are pressurized. Conversely, pressure vessels that are allowed to be pressurized within the range, when the range is live, and all humans are at safe distance from the pressure vessel or inside the bunkers. Human presence near commercial off-the-shelf parts is inevitable, so personal safety is also enhanced during those pressurized moments. An example of this is opening and closing an extra supply bottle. We use face shields, gloves, lab coats, and make sure that during these conditions that only the absolute essential personnel are around the rocket. Pressure vessels are designed to fail in desirable ways, so we make sure that we avoid hoop failure, and we tend towards, if there will be a event, that bearing or tear out failure is the preferred way of doing so. And here are the standoff distances for the range we're operating in for complex motors.
Go back to what's that motor designation? Is that?
That's just the name for every like doubling of impulse.
Oh, so this is
This is an amateur
a
code.
standard.
Yeah.
NFPA 1127 and NFPA 1125.
Okay.
Although, again, it doesn't cover like which, but that's where this is derived from.
Where are you?
We're at O.
All right, on to fire. The fuels that we use are flammable, very flammable. It takes fuel, oxygen, and a source of ignition to make fire, and it's good when it happens under controlled circumstances for a rocket engine, which is desirable. But it can also happen if fuel spills into the environment, less desirable. Fire extinguishers and water or sand buckets are always kept on site. If the test sites are cleared of the test sites are cleared of organic matter to avoid brush fires, and if the fire is contained, it's much easier to control. Fires can persist after static fires or launches, so the rocket must not be approached immediately, less than 5 minutes after last indication of smoke. Also, nitrous oxide. We also use nitrous oxide in a rocket. It decomposes into nitrogen and oxygen when heated, so oxidizers cannot be used to fight these fires intentionally or accidentally. When nitrous oxide decomposes, it releases heat and potential for a chain reaction, and rapid increase in pressure is present. So nitrous oxide will decompose around 1,000 degrees Fahrenheit, so presence of catalysts like fine metal particles will lower this temperature. Nitrous oxide can also decompose from adiabatic compression, which is caused by valve slamming and close, cavitation. All valves, excluding auto valve, can be actuated remotely to reduce risk of this happening. We have a new demonstration of a boiling liquid expanding vapor explosion. Not the highest risk, but it is a risk to consider. It occurs by sudden large leaks of rapidly flashing nitrogen gas. When this happens, the bulkhead bursts out, tank ruptures.
Oh, there was no sound.
Oh.
Oh well.
Once again, no sound. Fuel air explosion occurs when fuel vaporizes into an appropriate volume of air to reach explosive threshold and get ignited. Alcohols and similar compounds that we use do not vaporize quickly enough when outside. Fuel should be handled in well-ventilated areas to avoid this risk. Electrical hazards. Propulsion systems use a variety of electronics across a range of voltages and currents. The biggest risk here is the wire shorting and causing any surrounding material to ignite. There's also some risk to disrupting humans, but not as great. Also, the electric matches we use to ignite the engine can fire prematurely if not properly shunted in storage. To burns, yeah. The rockets generate a lot of heat. People can get burned if they touch something hot, like the nozzle after firing, and time must be given for everything to cool off. E-matches can also cause burns if handled improperly. And on the flip side of this, frostbite. The expansion of the fluids causes everything around it to cool down and gather frost, and can't touch with skin, or else it's going to get stuck and might get frostbite when handling it properly. Onto fumes again. Volatile fluids, which includes both fuel and oxidizers, always evaporate into the air. High concentrations of chemicals in the air can cause a variety of symptoms. Large amounts of gas, even if safe to breathe, can displace oxygen from the air and can cause asphyxiation. Pressure vessels can leak when rapidly changing temperature, going from hot as air conditioned to a conditioned car. We can mitigate this by fully tightening every valve on the supply bottle when hooked up.
Just a couple real quick. You're pressure testing the tank. What are you doing about pressure ratings? You're testing on the rest of the plumbing that's handling the gases and the like, the high pressure gases.
Mm-hmm. Well, for the rest of the system, I think we pressure tested similarly.
The COTS components are rated above their MEOB. We looked this up, and I think a lot of the ratings include a factor of safety before they will fail, at least on the places we buy them from.
Which are usually, most of our plumbing components, feed system stuff is almost entirely from McMaster-Carr. And when they have a displayed maximum expected pressure, we found that it is, they do also.
They usually like bake in a rating of like 4x. So they would fail 4 times what they say they are rated to.
Okay.
And we have proven up to pressures as well.
Okay. How long with this larger tank? I know it is always venting. How long does it take to vent the tank if it just sits there?
So this new tank will not be a constant vent. We'll talk more about that later, but
if it were to vent out of the vent valve only, it would probably take over an hour. If it were, but it has an emergency dump valve on it that's designed to be pulled with a very long string. That would vent the tank in under a minute.
Okay, well, the reason I ask is because you said 5 minutes, and I'm just making sure for your 5-minute dwell time before you approach the rocket that in fact you're going to be venting, that the tank will be vented before you approach.
I think that 5-minute number was about if there was a fire, because we have pressure in the rocket and won't approach until it's equalized, or if we don't know the pressure, then we'll pull the dump valve and wait.
and if for some reason that fails, then, well, Rick has a fun.
Yeah.
Yes, they have, I think it's rules and.
It's all in their rules and requirements, yeah.
It may be linked in the.
It is linked in the supplementals, but it's like a 70-page document.
Yeah. The majority of the rules are for safety in launch and safety in pressure vessels. So for things like ensuring proper speeds off rail, rockets can be stable, etc. And then a lot of it is for some of the same requirements that we've just described. Most of what we put on screen has been derived from the far out rules and requirements.
Does FAR have the 2,000-foot capability for standoff, or are you relying on bunkers instead?
They have
Bunkers.
Bunkers.
Yep.
Yeah.
So how far are you actually away from the rocket?
It depends on
Within 600 feet.
Yeah. Yeah.
Because the far side is only 700 feet on a side.
Yeah.
Again, just as you might want to update your charts when you talk about the safety, because you say 2,000 feet, but the reality is you're not going to observe 2,000 feet at FAR.
Correct.
Yeah,
For
that
our
was.
static tests. We have a site that's about 45 minutes west, which
I've been to
I've
the site, yeah.
But for reference, there's a site in Sorita that we've been doing our static tests that we also intend to use for this campaign. And on that site, we do not have bunkers, so we will actually be observing the stated standoff.
I know it's painful, but you might want to just make a spreadsheet of those requirements.
Okay.
And have it listed very explicitly how you need it. Because there is inevitably going to be questions that come up at the last minute. You want to be able to pull that up for every line item in that regard. It's painful, 70 pages, and a lot of line items. and safety is gotta be just the very first priority.
If you need someone to help, well, once you've done that, to look at it as you do it, yell at me.
Is that all for questions of overall?
So the overall system, do you do a pressure check on the overall system when you make or break any connections?
We'll do pressure testing on the tank and the engine as well, where we just
How
plug
do
the
you verify
nozzle.
connections?
Like between different tubes in the system. As for pressure rating, that would typically be done with we could do a CO2 test for that. I don't know if we stated this in the presentation.
Verifying connections is a difficult one when you're splitting between things that you have to test separately. I mean, in principle, we can pressure test the entire rocket at once and plug up the nozzle, so there's only one thing there. But I don't think we can do a hydro test with that. Maybe we can. The best I was sort of expecting was a shop air test, and then we will just pray for minimal leaks. Have our procedures for tightening everything, and make sure the best we can that it won't leak. And if it does leak a little bit, that's okay.
A suggestion would be for a leak test, would be perhaps to use dry nitrogen, maybe just 10 or 15 psi, so there isn't a significant pressure safety hazard, and do a leak down test. Basically pressurize the system to some pressure, 5 psi, 10 psi, and basically look for a pressure drop. Let it stabilize first, because temperature and the like will change the pressure. Let it stabilize, and then once the pressure is stabilized, say, look for the pressure drop over, say, 10 minutes, and then you can do what an equivalent leak would be.
Sure.
Does far out have a requirement on making and breaking connections?
They require that you prove your tank won't explode under pressure, but about connections there isn't a requirement. It's on you, I guess, if the rocket leaks a bunch.
Which did happen in that competition.
Yeah, it happened to several rockets.
Are you using torque wrenches, and what kind of fittings are you using? Are they AN, or what are the fittings?
We're going to try to prioritize AN fittings and NPT where we can.
Yeah. So just some other suggestions is, are you torquing fittings? They'll have consistent fittings. Is torque test. Make sure that you're inspecting the flares on the fittings for any damage. If you have any O-rings as part of the system, then consider whether or not you need to replace O-rings after every make or break operation.
All right, moving on to the engine. Are you doing this or am I doing it?
I think you can do this.
Okay.
Parts of the Sims under Jeff, but I can take over for the Jeff ones.
Thank you. Get out of here. All right, basic requirements for the engine. There's an error on there. Sorry. It should say 1,000 pounds thrust. So it's a 1,000 pound engine. It must fit within the 6-inch airframe. It'll have an ablative liner. The throat will not erode, so that we can get thrust from chamber pressure a little easier. And it'll be an impinging injector. Those are basic. Ooh, this is really hard to see. That's sort of what the engine looks like. The injector manifold is here, and the liner, and then the nozzle. That's the nozzle retention, and that's the thrust structure there. And the nozzle will be made out of copper in an attempt to sink all of the heat from the firing without any active cooling. So here's a little diagram. 10 seconds. here's a diagram of the motor and the entire propulsion system. The nozzle, chamber, and injector manifold are all down here. The igniter is a cartridge that holds a small solid motor, and that sticks in. It has a chamber pressure transducer sticking into the top. The two main valves are here, as well as the dump valve and the fill valve, or the fill port. And then we have the concentric tank design with the fuel tank in the middle, the oxidizer tank around the outside. The piston applies the self-pressurizing of nitrous oxide to the fuel with a moving seal where the piston pushes the fuel out the bottom by the gas pressure coming from the top. And then we have reaction control system with two valves plus a solenoid vent valve, and they are all directed up here for making thrust. So to compare it with Sonoran Wildcat, which is our last rocket, we'll have in the chamber walls a more mass efficient ablative cooling rather than heat sink cooling with really thick walls. We'll have a more complicated injector that should give us more effective mixing, and we'll have a higher mixture ratio for more efficient combustion.
Go back, threw me for a loop on the RCS. What is that?
We'll have a whole section on that.
Okay.
We could probably just hold off until we get there.
Sorry.
Here's the numbers comparison. We're about 4 times as much thrust, higher chamber pressure, higher throat and chamber diameter, of course. Predicted slightly higher specific impulse. In reality, it'll probably be about the same. A little more symmetric injector with 16-way symmetry, and the rest of it how it goes. That's a 2-scale size comparison. It would have been helpful if we brought the engine upstairs, but we did not. We can go look at it after.
Yeah, just want to go back one thing on your numbers there. You said 1,000 pounds of thrust, which if I've got my numbers right, multiply that by 4.45 gives us newtons.
Okay.
So it's 4,450 newtons.
The curve of the burn curve of the motor is going to have a
This is a detail of the injector. You can see the oxidizer in blue and the fuel in red. It has 4 holes going into these holes that inject for the fuel, and then on the next slide will be, or in 2 slides, we'll be able to see how the oxidizer gets in, but there's a separate manifold in the middle that it goes around and shoots. I don't know, we'll see it soon. That's what the injector face looks like again. You can see the O-ring grooves for the fuel manifold. That's the fuel manifold around here. Those are the bolt holes for mounting it. And this is what the manifold looks like, where there's this piece here on top that seals in the oxidizer manifold, which is all around here, and these are all the oxidizer holes. And then those 2 holes are for the chamber pressure and the igniter. Here is the chain, like a little closer look at the chamber. It's pretty straightforward, just a tube with radial holes in it and another tube for the liner. It'll be sealed with RTV silicone to prevent leaking around the sides. The interfaces with the engine, it's a 5-inch outer diameter engine in a 6-inch airframe, so there's these little spacers to connect it to the thrust structure here. And then, of course, it's connected to lines, which I think will replace these with flex hoses because there's now enough space in the design, that connect to the fuel main valve and the oxidizer main valve, as well as here's the igniter, there's the chamber pressure port. So we're now going to look at the modeling we did on the nozzle to see if it would melt or not. We had made perfectly optimal models with best possible performance and, the works, just to get the worst case. And they produced very perfectly optimal results that we don't think are necessarily realistic, but it does sort of show what we could be dealing with. So we were looking at 2 different materials, or 2 different types of nozzles. We had the idea of a graphite throat with an ablative outer part, or a copper nozzle. The graphite would be good because graphite melts at like 1,000,000 degrees or something, or much higher than our engine temperature, which copper does not. They're both very conductive, so they'll transfer heat into themselves, and so that no part will get hotter than the rest. But the main downside to graphite is that nobody will machine it. We don't have the tools to do it ourselves. The school won't do it. No shops in Tucson will do it. So it's a very challenging thing to try.
Temperatures and plugged them into ANSYS Fluent, which gave us some of the fluid dynamics through the shape of the nozzle. Then he then used ANSYS Transient to actually give us rough temperature values for the copper, and that is where these numbers are coming from. And
that's here.
Oh, that's these ones.
That shows that's sort of a loop showing the heating of the nozzle. You can see the heat mostly is coming out of the throat, but it's all evenly distributing itself pretty quickly. And this was with the potentially more realistic combustion scenario, and it only reached 1,000. We've done on the last rocket, Sonoran Wildcat, but we're gonna put a little bigger motor in it because the engine probably needs a little more oomph to light it. So we're gonna go from A motor to a C motor.
4 times the total impulse on the motor.
On a much smaller engine diameter. So they were having like a 3-inch diameter engine. We have a 5-inch diameter engine, so it's a lot easier to fit everything in.
And we worked with the machine.
Chamber wall is aluminum. Everything is aluminum except for the nozzle's copper.
Okay. Which aluminum is it?
6061.
Okay. And you're saying that nozzle, I don't know how quickly it's going to stabilize at 1,000 degrees, but your O-ring for sealing it to the thrust chamber, how is that going to take the temperature? And what is the O-ring?
They're the high temperature silicone, whatever they call O-rings.
Is it Bunin? I forget.
It's not Bunin. They're the seem to be the standard for other liquid rockets, and I don't remember their rating number though. But
For the nozzles, it was the standard?
Mm-hmm.
Well, I really have a question about that. I'm not aware of what rubbers. Now, again, you're short duration, but I'm not sure what rubbers are going to be happy at 1,000 degrees.
Right. Okay, I don't see them on the slide, so we'll make sure to double check that.
If you design it correctly, especially the way the O-ring senses the pressure, it should never get to anywhere close to your combustion temperature.
Yeah. Hopefully.
So do you have a detail of the interface of the nozzle to the case?
Here, I guess you can see.
That liner is the brown and
Yep. And the
so
chamber.
there was silicone in between that liner and the copper.
Yeah.
How are you going to assure an even coating all around?
Of the liner?
Yeah.
You mean like even thickness of the liner?
No, we're
Of
going to
the-
put silicone around it. How are you, sliding the parts in there to say it's all going to be nice and, covered fully?
I think we'll probably just overdo it a little bit. That's
It's a friction fit, though, definitely not so like weak response.
it's well, so the silicone will only be here and here. It won't be around.
Okay, it's not around, so it's friction fit, or there's no gap essentially between the liner and the chamber.
Yeah.
I really think that your package here, you really need to talk about the O-ring design and interface, as far as how much compression on the O-ring, what the material is, because that's an extremely critical element
Okay.
on this motor. I would say, I would call that an action item, that you really need to address that.
Okay. Colin, got it? Yeah. Great.
Anything else?
So I'm an open joint fan. I don't like sealed joints.
I got it.
The way you have that set up, it becomes a sealed joint. What I mean there is that the silicone ends up taking the pressure, not the O-ring. You gotta try to avoid that. A lot of it's going to depend on how much gap is between that liner and the copper when you build this thing up. And if you make it too tight of a fit, you worry about pressurizing the volume in front of the O-ring, how that gets pressurized, avoiding jets, evenly pressurized during the ignition. You address this with any of your other motor designers. I agree. You need a complete evaluation of that seal design. Gaps. Where the silicone goes in there.
Can you just go back to the cross section there? So a couple things too, just during assembly. Silicone O-rings are relatively soft. They are easy to damage. So I would put whatever assembly procedures that you have. You may want to look at some chamfers to help assist this, to avoid nicking or tearing the O-ring. What lubricants are you going to use on the O-ring? Compatible lubricants, possibly high temperature lubricants. So again, that whole seal O-ring design needs to be really looked at.
Sounds good.
So the hardware that keeps the nozzle in, how many, it looks like a pin or a bolt, is that a ring then?
Yeah,
5/16 bolt.
it's a bolt ring that holds it in with a separate.
Those
Go to the
spacers?
igniter slide. You should be able to see that at the end. Oh, wait, just past it, I think.
Yeah.
Yeah.
The interface.
Yeah.
You can't really see it, it's pointing the wrong way. But there's a bolt ring here that holds it in with a retaining ring.
How does that happen? Is it a 360-degree ring?
Yeah.
Yeah.
How many
It-
bolts?
8.
You looked at the total pressure on that, 400 psi across 6 inches. That's a lot of pressure.
Yeah, I have all the calculations,
Just further down.
and it,
As far as shearing those bolts out.
because they're 5/16 bolts, it should be expected to fail well above 400.
I believe we did that.
I didn't put the calculations in the slides.
How far are the bolts from the edge that it's not going to tear out?
That's also in the calculations I did. I don't know the number, but it is more, it's like more
Is this
than
the
the
one we did a while
diameter of
back
the hole.
together?
Huh?
Is this the one we did a while back together that Desmos or something different?
No, I don't think so.
Okay.
But
Are you pressurizing that pressure vessel? Or that combustion chamber?
As a pressure test, like a proof?
yeah,
How are you proofing I mean, are you going to put a dummy nozzle that's plugged in there to pressurize it, or is that how you're applying the pressure to the system?
yeah, we'll just probably end up replacing the nozzle with a similarly shaped plug.
Okay. Well, it's really critical here is not just is that sealing interface, that whatever you use as a dummy nozzle, it has to mimic
Yeah.
your sealing convention.
Mm-hmm.
You may want to add that to your schedule too,
Sure.
if that's not on there.
Chamber
There's
pressure test.
There's chamber pressure test.
I use that. That's what we're requiring for pressure.
Okay.
It's up to you how you want to pressurize it, whether you want to pressurize it through one of the inlet ports, or whether you want to cap those and do a dummy nozzle and pressurize through the nozzle. Up to you how you want to do it, but all the interfaces that are retaining pressure need to be right. They can't be dummied up for test.
Yeah.
Sounds good. Could that probably take a block of stock material at the back, block that in, put a port on the bottom for dummy nozzle with this port in it? That'd be good. Hydrostatic.
Mm-hmm.
Okay. Oh, we have that note.
What's that block of aluminum weigh?
40 pounds.
40 pounds.
Oh, the copper?
That copper.
Yeah, the copper is about 40 pounds.
The nozzle, that was one of the other downsides of copper, is that it's way heavier than
Way
graphite.
heavier.
It's like 7 pounds versus 2 pounds.
The machine nozzle will be 7 pounds.
Something like that. Do you want to talk about feed
Yeah.
system? Okay. Feed system.
So we do have a valve lead, also Jeff Busker, the same person as the Sims who's currently in class. But I'll take over for feed here. So for our feed system, we have some requirements. We're using servo-actuated ball valves for to control the flow, similar to the prior rocket, Sonoran Wildcat, which has been proven with similar designs. We did need a larger size valve for this one, so we'll have to do extensive testing of the novel design. But based on that, servo-actuated. Feed system and all valves will be using appropriate pipe fittings so that pressure losses are minimized so that we can still get to the proper values for combustion. Onboard valves will also be controlled by the rectangle. And during our fill and fire process, we have the ability to either automate or have manual buttons through a graphical interface, which will be on a laptop. Talk more about that later through the onboard computer. But those will be controlled either manual or autonomous. We can do both for testing and figure out which one we like the best. Although ideally for actual staging, we can do most of it autonomously. Feed system fittings will interface with the machine parts and valves with NPT, because we can't really put a flared fitting on a block of aluminum or copper. So where we have to, we're using NPT. Otherwise, we're using flared elsewhere, and that gives us the ability to clock components around. You'll see more about that in a sec. Valves. So here you can see our novel servo-actuated ball valve design. Servo with some gears attached to it. Above the white one is the half-cat prior rocket, which we've demonstrated works. And that one is 1/4 inch NPT ball valve, which works for that one. And we actually will be using these for the RCS system, which, again, there's some more information about that later. Whereas we had to use 1/2 inch NPT valves for this rocket because so much more fluid, so much more to move. So that is that. Here's our plumbing and instrumentation diagram. The major change from the preliminary design review is that we have the igniter controlled by the rec PC, which actually, as you see there, the rec PC that's on the right side there is the same shown here. The rectangle is an onboard flight computer, not exactly doing anything other than roll control, but more about that as well. We have another diagram of the self-pressurizing nitrous piston design, slightly different from the half-cat design. Half-cat rocket had one long pressure vessel with a piston between.
There's a slide about that.
Oh, there is? Okay. But for us, we have nitrous, which will be liquid down below, and then gaseous, so it'll self-pressurize onto this piston, which the piston will then push fuel out into our two main valves where we got liquid nitrous, liquid fuel going into our engine, controlled by the rectangle computer, where we're also measuring pressure in the chamber, in the tank, and we have available ports for other locations if we need. On top, these two servo-actuated ball valves control the clockwise and counterclockwise roll control of the RCS system. Pressure transducer on the top here is which we're measuring the gas pressure, which will be useful for the roll control to tell us when we're out, and will also tell us when the rocket is safe to approach. We also, in case of an electrical failure and all of these electric valves do not work, we have the manual dump valve that we can pull from the string, as described earlier, that in the worst case scenario, we can depressurize it at least from some reasonable distance. On top here, we also have a solenoid valve, which is a normally open solenoid. So again, in the event of an electrical failure, the solenoid will open, loses power, will open the valve, and will slowly begin venting out our nitrous. So even if we detect that, I mean, if the rectangle loses connection, it dies, and we start to see it venting, we know that it'll, in X amount of time, safe to approach, and pressure will be down. And as we approach, we'll also most likely pull the dump valve. As well, check valve for fill. It doesn't back pressure when we disconnect and vent the GSE. The rectangle itself is controlled by a radio link, which we actually have some modules here, which I'll talk more about later. Pressure transducer in the ground support equipment feed, which Alexa will talk about a little bit more later. But we have pressure inside of the ground support system, which roughly tells us the pressure of the nitrous first. Then when we know that the nitrous bottle is at a safe pressure, it's not supercritical, anything like that, then we are clear to actually open the servo valve to fill the tank. And then after all said and done, we have this secondary valve here to a static or atmospheric vent that we use to de-energize the lines of the ground support equipment. This piece shown here is a quick disconnect, which we're using the same design as from the half-cat rocket. So this might be a limiting factor for our fill time, but that's actually okay for competition requirements. This will just disconnect when we actually lift off. I don't know if we're still using a Teflon pipe or something else, but same quick disconnect design as half-cat rocketry has proven with the Sonoran Wildcat design.
How do you fill the fuel?
The fuel is something that we'll pop open the top bulkhead for, and no, different?
Well, we're gonna siphon it up by pulling a vacuum on the tank.
I forgot about that one.
Because or we open the tank at the bottom, push the piston up, and then pour it in. But it's a sort of involved process. But it's not. It doesn't need to be. It's pressurized by the nitrous. So.
Yeah, I mean, the fuel loading is done beforehand. Nitrous is. We're all backed away, but for the fuel itself, it doesn't create harmful vapor, so we are able to just pour that in by hand. I mean, ultimately siphon and use the piston, which I apologize, I forgot about that one.
You're going to cover the piston design?
Yeah.
Yes.
That's the next slide.
Yep.
So how do you bleed the system when you fill
You can go back one more. The solenoid valve here is also controlled electronically. So during the fill process, we'll be opening the solenoid and as well as the RCS valves up here. Really whichever ones we deem necessary for it. These have a lot more flow than the solenoid. So most likely during our fill procedure, we'll be opening up the RCS because these double as static atmosphere vents. This is mainly added because in the PDR, it was deemed necessary to add some sort of passive relief in addition to the dump valve. So the solenoid we have controls over, as well as these servo valves we can control for the vent, the gas, while we're filling.
One thing on your instrumentation here, for your grounded testing,
Yeah.
I think you need some temperature data, major predictions on the nozzle, how hot it's going to get in the. So I would recommend strongly that you put some thermal instrumentation on there during ground testing to characterize the system.
Okay.
The other part of it is for even just have ambient temperature knowledge, because again, the nitrous is kind of like the sweet spot of like 70 to 90 F. And if you're going to be out in California at the end of May, you may not have 90 F.
Right.
You may have a lot more.
There actually is an ambient, it's a barometer and a temperature sensor at the same time. But otherwise for engine temperatures, we don't have that yet, so I'll double check and see if we add that. Otherwise, if it's not on board to the rectangle, I'll definitely make sure we can add that outside as a sensor.
At least for static testing.
Yeah. Thank you. And as for the piston, so our rec rockets so far, as well as this means last year's and this year's, use the dual acting vapor pressurization, which means the nitrous pressurizes itself, which pushes on the piston, which pressurizes the fuel, which means that we don't need nitrogen, we don't need a pressurant. So instead, that is that. Saturated vapor, the liquid is on the bottom of the tank, gas is on the top. Covered it a little bit in the last. And then, yes, as the liquid drains, it keeps itself pressurized by turning into gas. And,
So one question, when you actually operate the system, do you have any red lines for, you know, either do not go under a certain temperature or above a certain temperature because of the characteristics of the nitrous?
Right. So for the characteristics of the nitrous, our max pressure is around, it depends on the ambient temperature, but we can roughly gauge the temperature of the nitrous based on the pressure. There's a vapor table that we use currently.
It's because it's on the vapor curve.
Yeah,
Yeah.
we can flesh it out if that doesn't seem like a good solution in the current time. Otherwise, we use, for at least our higher end of pressure, we use a vapor chart table to determine based on the current pressures in the tank, assuming it's got liquid. This is the state of the nitrous, and we avoid supercritical. As for a low end of minimum engine operating conditions, I don't know if we have fleshed that out, but that's a good one to make sure we put in the procedure.
Again, you need to look at, you know, as part of launch discipline, you need to establish your red lines that
Right.
are, do not exceed or do not, you know, don't go outside your red lines. If you're not there, you're done.
Yeah, the main
Yeah.
one is the MEOP.
Yeah.
That's set partially for the tank burst factors of safety, but also partially for if the engine performs too well, then the meaning the chamber pressure is too high, then we'll have problems. So, yeah, the
Right.
MEOP 870 psi.
We could even automate the process where if the onboard computer detects pressures above, it will immediately vent. We can have that as well. Stacked piston design. Here's a better demonstration of what that piston looks like on at least last year's rocket, where you have this piece here is the movable piston with double O-ring seals. So
Here, if you want, I have the current one.
oh, here's the new one. So fuel is loaded prematurely, or before we pressurize. You got the liquid darker color here. The gas will be up here, which pushes on the piston, which will start at the top. Both of our valves, if you remember, are down here, so our feed system goes straight to the engine. So minimal, no downcomer, no anything like that. We fill it up, pressure, liquid high pressure. We're able to vent from the top until we reach that top fill process. Then, as we fire, the liquid will sort of turn into a blend of vapor and gas, which keeps the pressure high, pushing the piston down. Now this is different from last year's rocket because it is now concentric. You can go back one slide. The prior rocket, which has been tested very thoroughly by people other than us as well, used a single shared tank with a piston down the middle. But we haven't fully tested the concentric design, so we're going to make sure that we do. But otherwise, this is a proven piston design for a shared tank.
Is there a physical stop at the top of your?
Yeah. There's stops at the top and the bottom. Oh no, I've entered the text box.
So when you do your safety pressure testing on the tank, are you putting liquid both inside the fuel tank and the nitrous tank, so it doesn't collapse?
Right.
Are you?
Yes, we will. We'll be putting, as a substitute for our fuel, we typically use water. And as we're doing a hydrostatic pressure test, we'll probably still use the piston, but then put water in both tanks, and then just a little bit of air to pressurize. Yes. The reason we're able to use much thinner walls, I don't know if that's in there yet. That's tank, actually. That comes later.
Yeah.
But we'll talk more about the walls.
So just going back there too, just for, again, not knowing what the mixture is on this, do you run out of fuel first, or you run out of nitrous first?
You run out of fuel first always because, well, you ideally run out of liquid nitrous and liquid fuel at the same time. And then,
Oh, yeah.
but if you run out of liquid nitrous first, you end up in this like sort of gas phase burn where you're burning gaseous nitrous through the engine, and it makes a lot less thrust.
It still does make thrust. but
It
less.
does make some, but not much worth counting on, in my
Right.
opinion.
What I'm getting at is, do you have a situation where there's a significant differential pressure between the fuel tank and the nitrous tank?
There never should be because the piston is
piston.
always free to move.
Yeah, there's no electronic control. It is a purely mechanical system. So by the nature of there being a difference in pressure, the piston will push across. I guess the only situation where I see that happening is if the O-ring gets like messed up, or if there's other parts that have pieces sticking out that artificially stop the piston, and then that allows a pressure difference to build. That could be bad, but otherwise should be passive for that.
And are you, between your various tests, are you tearing down the system to look at the O-rings and the like to make sure that you are not abrading O-rings as it goes down the tank? I'm not sure if you've specified any surface finish or anything. Is that slides that you're not, or is it just a piece of pipe with whatever it's made with? No, I'm a little bit worried that you may start damaging O-rings
Right.
and start mixing propellant and oxidizer.
That's a big concern for us too. So for the half-cat rocket, we would switch it out every couple of fires, but for this one we're going to be a lot more rigorous. And I think we definitely expect after every fire, or every engine test. For this one, minimum at least swap every single time for the first couple ones until we get a better feel for the condition of the O-rings after firing.
When you say O-rings, there are multiple O-rings on that piston?
Yeah. Redundant seal.
There's multiple O-rings on also the bulkheads as well. That seal between the fuel and oxidizer.
Again, since sealing is critical in this design, I would like to see, for any future presentations, a little bit more detail on the gland design for the O-rings. How much compression, what materials.
Okay.
Okay. There's a little bit of detail in this tank section here.
Okay.
Are you doing this or am I doing this?
Either way is fine.
Oh, you got this.
Okay. So here's some requirements for the tank. Tank is fitting the 6-inch outer diameter for the airframe. Sub-minimum diameter motor. The tank is the diameter of the rocket. The tank shall be concentric design, which we've just discussed a little bit, where the fuel's in the center, oxidizers on the outside. Tank has a MEOP of 869, so will be proof tested to 1304. Tank closures will be bolted with radial bolts, and we'll talk about the bulkheads top and bottom, the bolts, as well as the calculations for that based on the half-cat rocketry pressure vessel design, which that rocket's been tested, so we've trusted this. Tank shall be able to be depressurized with a dump valve, which is a very long string, and we also have that solenoid in the event of an electrical failure. Next, the bulkheads and pistons shall have redundant O-rings and seals between the fuel and oxidizer in the environment, because we really don't want that mixing. The tank shall also not exceed the volume which could provide more than the legal amount of impulse where we would be considered a Class 2 rocket for FAA. So we got to keep it small enough that we don't have to worry about those requirements. Tank is also not larger than practical to transport, which it's kind of approaching the limit, but so far so good. Right now, available equipment allows 8 feet max tank size, and when we break down the rocket into those pieces, this will fit into that. Tank is also vented by a normally open solenoid valve, which we discussed in the PID, and the pressure, onboard pressure transducers, which we also talked about. Here's a comparison between the Sonora and Wildcat. So 4-inch class versus 6-inch class. The tank walls are both 1/8 inch thick, if I remember, fraction, and 3 feet long versus 6 to 8 feet. That needs to be updated. It is actually 8 feet. And concentric stacked, we talked about that too. And this one will have 16 bolts now that it is a 6-inch class with similar pressures. And our impulse class does go up to O. Prior design had a static vent, which was just a hole in the tank, so it would always be venting nitrous. Now for our RCS system and our performance, we decided to go with an automated solenoid valve plus the dump valve, so we can keep some of that gas left over, which we will still talk about later. And the MEOP change was originally 1200 since at PDR, and now it is brought down to 869 to stay well below the supercritical limit, as well as other combustion requirements. The change is, to satisfy chamber pressure targets. Mainly, I think that was driven by thermal sims, if I remember correctly. I don't recall.
Yeah, the models were saying that we would have a lower than expected pressure drop across the plumbing, so that we lowered the tank pressure to keep the chamber pressure the same.
And this gives us good burst safety. About the concentricity. We kind of already talked about this, where the fuel sits above, or sits. Okay, so Northern Wildcat has the fuel above it, and then they use a downcomer. We do not. We have concentric tanks with, as we kind of put the diagram earlier. I guess I don't need to go into too much detail with this. Seems okay. Then inch concentric. Yeah, here's the comparison of what these tanks look like. I think this is to scale.
Mm-hmm.
Yep. So it's much larger tank, way more propellants in this. Okay, here are the bulkheads. So here's our redundant O-ring grooves on the inside and outside for our piston, or for our aft bulkhead. We've got several ports on the right side, as you can see, for our dump valve, for the fuel output, and the main oxidizer output. And then over here we have our fill input, which goes to the quick disconnect that we had. Yeah, we got the 16 radial bolts are put into the side here, and I think they're just 5/16. Yeah. The forward bulkhead is very similar. Again, we have the redundant O-ring grooves, and this is also where the start of the concentric tank is, the start of the concentric tank. We got the same set of poles. We got more now for our RCS ports, because we got those extra valves shown in the feed. We got the vent valve for the solenoid, which is another port in the area with the gaseous nitrous oxide. Then our recovery mounting point goes into here. I haven't been as involved in recovery, but to my knowledge, this one is a very large threaded rod that goes straight into this bulkhead, and this will be a main point where we can transmit a lot of force to the whole tank assembly as well. And of course, pressure transducer at the top. And
Are you using Loctite for that recovery bolt, make sure it doesn't back out?
yes, and there is a section on recovery too.
Yeah, this is a mirror of how it's done on the original half-cat design, where they have a sealing washer here, and then a bolt that sticks up, and then a coupling nut that goes to whatever is above that. So you can tighten the seal on this face very well.
One other question, your solenoid valve, have you considered just orientation, that G-forces don't open it
Yes,
during acceleration?
it's oriented.
Perpendicular to
The path of the valve is going up, so the closing of it is perpendicular to the.
So the mechanism is perpendicular to the highest G limit?
Correct.
Yeah. And then this is sort of just this big chamfer here is a guide for getting the concentric tank aligned correctly. There is actually, the concentric tank only extends up to about here, so that's how the gas flows into the sides and pushes down on the piston. These are our factors of safety calculated for the different failure modes. And that's it for the tank.
Do you have detail on how that center tank is held within the scissor tank?
I don't know what slide, but it's held at the bottom with O-rings, and it's held at the top with that. It bumps up against the bulkhead. There's extra length, but it's not bolted in because there's no real force pulling it out.
Yeah,
And it's constricted
pretty far
from
back.
moving out.
I'll just bring us back to where we were.
Are you going to measure how much force it takes? I mean, again, for the fill tank, what is the wall finish on there? Is it just as the piping was built? Okay. Are you going to do any kind of force measurements, travel, make sure that the piston travels smoothly within that tank, and that it doesn't require unreasonable force to move it within the tank?
Yeah. We expect that it will probably take about 15 psi to move the piston, which
So
over
it's about 200 pounds of force.
Yeah. Well, like worst case during the engine firing. That's what's modeled for the pressures in the fluid system. So, but the center fuel tank should be able to hold a 15 psi vacuum.
I don't recall. What is it? It's not also an 1/8 inch, but
No, it's a 16th.
yeah.
Again, I would suggest a static test with no propellants or anything on there, just simply how much force does it take to move the piston? You know, are there any spots, any hard spots where it tries to hang up?
Yeah, it's good.
So I would definitely verify that, because if it hangs up or something, everything goes to pot.
Yeah.
Yeah, there have been pictures of concentric
yeah,
tanks
yeah.
that got flattened by the piston getting stuck. Another design feature that helps it not get stuck is the keeping it sort of long enough in the tank so that it can't get wedged sideways.
Right.
So the two O-rings are spaced apart, equivalent to the diameter of the tank.
All right. Is that it for questions on?
I assume you're using elastomeric, some kind of rubber O-rings on there?
Yep.
Yeah. I don't-
Buna and
Una N and white.
just Buna.
Just Buna N.
Yep, that's what we have been using. As long as you treat them right and replace them, they're good.
Okay, again, one of the issues I see with the concentric, are you lubricating of any kind in their tank? Because if you're doing any kind of lubricants, that's
Right.
going to mix with the
Yeah.
oxidizer.
I don't.
We use
Unless it's an oxygen-safe lubricant.
we use synthetic lubricant on the O-rings to keep it from having a problem with the nitrates.
So it's oxygen-safe lubricant you're
Yeah.
using?
Right, and this is the same for the at least the O-rings and the lubricant. It's the same that we've been testing successfully with the Sonar and Wildcat design as well.
Okay.
So
Yeah.
should be good.
Half Cat Rocketry this weekend reached their 100th successful static fire with that design,
Okay.
which is kind of cool.
That is nice.
All right, rectangle.
The rectangle. So the rectangle is the onboard computer which controls and measures a lot of things. Here are what data we are recording. Pressure in the chamber in the tank. GPS location and altitude. IMU for acceleration, gyros, and magnetometers. Barometric altitude, which has also got a barometric temperature sensor built into the same unit. Reaction control system status, as well as the valves for solenoids and main valves. The flight state, whether it thinks it's ready to fly or not, and if it's in recovery or not. And there's potential for other expansion if we want. The rectangle itself, the purpose is mainly to actuate the valves for the engine and RCS system based on our remote commands from a safe distance, as well as onboard logic. For example, if we set a max go, no-go, we can have it vent. The rectangle will also attempt to control the roll of the rocket using RCS thrusters, which are cold gas thrusters using the excess nitrous oxide from our burn. It'll be taking inputs from the IMUs and pressure transducers, saying how much pressure we have on those cold gas thrusters, and it'll be running an onboard control system to actually do that. I believe we have a section specifically for the RCS again.
Yep.
And the rectangle will be placed somewhere above the tank, which was above the RCS system in this current design, and will be kept from taking up too much vertical real estate. There's more about it, but it's basically saying that we need to be able to talk to it. It needs to have an abort and hold mode, which we can now do a hold mode because the last one had a static vent. We couldn't. Now we can. And we need to be able to do all of this remotely via radio from a long enough period of time that if we don't have external power, we can still hold for more than we ever should need to and still have remote telemetry and controls over everything. It'll also be connected to ground power and have launch from just a little breakaway connector, and that will just ensure that it can stay topped off and powered up. We will disconnect we can have a thing to disconnect the ground power shortly beforehand so we know batteries are good, but that'll be more in procedure. And then remote commands to also start onboard camera recording.
Oh, sorry.
So here's our architecture diagram. There's a lot of things on there, but I'll go through them quickly. Our battery source is going to be a 3S, so about a 12 volt pre-standard 100 watt hour LiPo currently. But as we do some testing and we figure out what the actual power expectations are, I anticipate we can switch to a much lighter weight 50 watt hour LiPo. Otherwise, that 12 volts then gets converted into a 3.3 volt, 5 volt, 24 volt rail for sensors, servos, and solenoids respectively. We have two different types of servo actuated valves, both of which run on the same 5 volts and the same PWM signals from our processor, the STM32. It will also be logging data to an SD card. It'll be using a remote telemetry link from XP modules, which we have already tested on other similar setups, which is why we purchased those already. And we have a ground station, which this board pictured here is actually this very thing. So we can already get started on testing some of the remote telemetry. For the pressure transducers, we have an analog to digital converter setup where we have 4 channels currently available for use with 0 to 5 volt pressure transducers, which corresponds to the models we are using are 0 to 5,000 psi. So that also connects. And then on a shared bus with these 3 sensors, we have a low G gyro, which is higher precision, has all 9 axes. In addition, we have a high G gyro for when we're under significant acceleration for up to 400 Gs. It is lower resolution, but can give us data when the other one might not. And then we have a GPS module, which we don't really need, but it would be helpful if we still have the remote telemetry. We can maybe see exactly where to go during the recovery process, assuming those boards also help. And that is that diagram. As for the PCB, here's what the current rectangle design looks like. We have the modules kind of all placed on the front to make assembly easier. It's 100 millimeters by 140 millimeters, which is also in the next slide too. Don't worry about it yet. We got servos, SD card, 2 different antennas, one for GPS, one for remote telemetry. There's the radio module, which we'll solder directly on. A battery if we want real-time clock. Some breakout ports for checking everything, and the battery will connect to this. But otherwise, it's just about layout, so that's not really a thing. We'll be using a 2-layer PCB, 140 millimeter by 100. Most of the components are surface mount, so about 107 of the tiny, various small ones are S&D. Then a few of them, about 24, including our pins, connectors, battery stuff. Mostly those are the through-hole components. We've tried to limit the size of them to not be like a 1201 or some other footprint. I believe the smallest size is a 0603 footprint. So they should be, it's difficult, but it'll be hand solderable. Front components only. We'll be using 1 ounce per foot squared of copper, and the minimum trace width is 1/4 millimeter, so current shouldn't be a problem. Radio setup, we'll be using that module, the XP 900 megahertz module, so it's unlicensed, we can use it. It's got a 1 watt max transmission power. I don't know if we actually will need it, but I figured we would need as much range as we can because the rocket might be at a weird orientation and the tanks are all metal, so in case the radio gets blocked, I wanted as much transmit power as we could get legally. This is our transmit link. We've already tested a version of it on a different XP module, but seems to work so far. We haven't validated the range, but it'll be nice to see when we actually put it all on board. You can go to the next. Manufacturing plan. So the main modules, like the power, the GPS, gyros and stuff like that, those are going to add up to around $100-ish from DigiKey, same website. And the radio modules are the most expensive part so far, but included a whole dev kit which had the ground station already on a pre-made board. So we went ahead and got that for $200. Other modules like capacitors and resistors, I haven't actually calculated, but it shouldn't be more than 100. They're very small, very cheap, less than $1. PCB itself, $60, and very standard manufacturing stuff. So we can go to them.
How many of these are you building?
Right now, we only plan to actually use the 1, but when we order a PCB, it'll give us 5 of those boards because that's the minimum quantity. But in terms of the rectangle itself, for now we're just going to build the 1 to start, and then if we want to make design changes, we'll do another setup with most likely similar components. Here's what it will look like mounting to the board. The green I've put as just rough dimensions for the battery. We have some extra room above it for the recovery. The board will mount sideways on top of an RCS system, which we'll see how that fits into the rocket, I believe, later. But just some M3 bolts, pretty nice. It slots in, and there's holes below it that we can put cables through. So I don't really need to go into too much detail about it, but it uses USB chip on board, and then it interfaces with the PC. So we can program it remotely or via a USB connection directly. And yeah, then are there any questions on the rectangle?
Yes.
Yes.
So first off, what I don't see here is any kind of a state diagram that shows it going from a pre-launch mode to a flight mode to a control mode, and what the inputs are that transition it from between the different modes.
Right.
So it has me a little bit worried. Have you really thought through all of the different modes and how all the different modes are actuated?
I guess not yet. I've been focusing so much on the hardware design that I guess I neglected the software.
Right.
We
I
have,
mean, is software supposed to be part of this? Because there's no software discussion at all.
not currently. This was mainly focused for me to get all the hardware ready so that we can do testing and figure out the modes that we want in desirable test conditions. I've had some of our members look into the software a little, but we haven't gotten as far as actual modes, so I'll make sure we look into that next.
Okay, because the other part is that really we'd like to see some kind of a test program for this. You know, a breadboard, not necessarily the final form factor, but to basically, you know, because you may have to make 2 spins at least on your board, or cut and jumper the board.
Right.
And I'm worried about what's your test program to make sure that this has, you know, what the power consumption is, that it has the proper drivers on it, the power,
Right.
voltage, all the above.
I do have a spreadsheet tracking the individual power consumption of the parts. I didn't put that on the slides here, but the servo valves at maximum have measured to be about 1 amp current, and it gives, with the 4 of them, max at the same time would be 20 watts. Plus the solenoid is, we don't have it yet, so we haven't tested, but that one's slated to be also 10 watts. And each of the microchips is in the milliamps or microamps of current, but in total, for a 2-hour battery life, that would give us a 100 watt-hour battery capacity.
I would make a generic suggestion for architecture on this. I would consider a 2-bus system. One is I'll call it a regulated bus, where your stuff that is constant load, like your microprocessor,
Right.
is run by that, and your sensors. And then I'll call it your pulse load bus, which is your solenoids and the like, where if you've got fluctuations on the bus,
Right.
they don't reset or somehow cause issues
So
with your
yeah.
steady state stuff.
Currently, all of the steady state stuff is the logic level, the microprocessors. Those all operate on 3.3 volts, which each channel has its own dedicated power circuitry. The only thing I haven't separated is the battery itself.
Okay.
But for also situations like the solenoids and the servos, I've also added, in addition to them being separate regulators, they also have capacitors on board to help support in the event of a high load. But fortunately, all of the regulator and step up, step down converter components are at least labeled on their data sheets to withstand more than the current that we are expecting to pull at a max.
Okay. Again, I'm not worried about them as much as just your wire sizes and everything else. How much you're going to pull down the bus
Okay, fair point. I'll
and
double
pull
check.
down the batteries,
Right,
that you don't reset anything.
right.
And again, you really need to do a rigorous test program because this thing is safety essential. So I really would need to see a rigorous test program. I think you should be considering at least 3 builds. Basically a breadboard build,
Right.
a version 1 build, and if you got, if the traces and everything change too much, and then a final spin on the design that reflects all your lessons learned.
Okay.
So I would say you have at least 3 builds here, and your software, again, talk to your software folks. Are they
Right.
going to incrementally build the software and add modules, or are they going to deliver, hey, everything's going to work out of the box?
Sure. All right, I'll double check. Currently, my only concern with that is going to be budget. So I'll have to talk with people after this and see what we can afford to do for a breadboard build. A lot of the components do exist as a separate chip module that you can plug into a breadboard, but unfortunately, those usually cost like 2 or 3 times as much, and you can see how quickly this adds up. So we'll see. We were having some money troubles. I'll have to talk to Kevin, who's primarily in charge of that, but that's a really good idea, and I would love to do a breadboard model if we can afford one.
I think you have to
Have to,
afford,
okay.
not can, it's, you have to.
Okay. All right.
All right. Anything else? Okay. Reaction control system. So this will be the payload of our rocket as far as the competition is concerned. The basic is that we are using the gas in the nitrous tank to spin the rocket back and forth in the hope of stabilizing it on the roll axis. We'll have thrusters in the range of 5 pounds of thrust. We'll have 2 opposing pairs so that they'll only impart a rolling moment, no pitching moment, so that the trajectory of the rocket won't be affected. And it will be controlled off of the rectangle and use the servo-actuated ball valves, which are the same valves we used on the Mojave Sphinx or the Sonora Wildcat. They're very well proven.
Will they act fast enough for control?
This is the unending question, and the current way of looking at it is that they'll be they're not going between on and off. They have the partial open states, which will be able to give a thrust profile, I guess, which is something we'll show later. This is a proof of concept. It's sort of a new development that, as far as we know, nobody's tried on a liquid rocket yet. And if it does fail after launch, it won't affect the trajectory. It'll either start spinning up, which makes it spin stable, or it will do nothing, and then it will be just like normal. Hopefully, the camera footage will be cool, but that's,
But you don't have, the control system, you have a control system evaluation as far as...
We have a little bit of control systems we'll talk about, but it's not finalized yet because we're still working. These were some early prototypes. Version 1 was way too high of a thrust, so we looked at something a little smaller for version 2. But now what we have is this wheel. It has 4 thrusters in their opposing pairs, all in one piece. You can see this one and this one both make the plus M by the right-hand rule, and then that's minus M. They're connected by these NPT ports. They've got radial bolts to attach it to the airframe and this pass-through in the middle for the recovery loads, because this is above the top bulkhead, so the shock cord will go through it and try to, not a little bit of side loads onto it, but no vertical loads. So this has all been modeled in Simulink. Simulink is very powerful for both control systems and fluid modeling, it turns out, because Simulink has a library called SimScape, which turns the Simulink signal lines into pipes. And it has models of ball valves for the sort of partial opening of them, but that will be expanded with CFD that we'll do, and eventually real tests. And it does the gas dynamic simulations of the somewhat more complicated than usual system. So we looked at 2 different kinds of valves for the RCS. We looked at solenoid valves, which is this slide, and servo valves, which I guess we kind of spoiled, we already ended up using. Solenoid valves have a lot of advantages. They fail open, if you buy the right ones, of course, which is a great thing for safety. And they actuate very quickly, so we can just have a bang-bang control system that will be very simple to code and, should be good. But they have a really, really low flow capacity, especially compared to ball valves, and they're really heavy. The maximum thrust we could get out of a solenoid was about 1 Newton, which is probably not enough. So ball valves, they're cheap, they're well proven, as we've talked about. They have a high flow capacity, but they're difficult to characterize. They require the more complicated control system, and so, a difficult time modeling, and they can fail close. Oops. So these are some preliminary CFD results where we show, I guess the colors don't really help here, but it's showing the different pressure drop between like 45 degrees or 35 degrees. We did 5-degree range from 0 to 90, and that I haven't seen the final results for that yet, but that'll sort of go to inform the Simulink model for everything. This is sort of an unhelpful screenshot of Simulink, but this is over here, it's modeling the gas system. Over here, it's modeling the control system. They have the very convenient 6 degree of freedom block for doing all the flight simulation, like the, equations of motion. There's no control system in this right now. Right now I have it separated. I have it just measuring the angle, the thrust with respect to angle of the valve, which is this. This is thrust in newtons versus angle in degrees. So 0 is open, 90 is closed. And you can sort of see that it's at the low angles where the flow is limited by the nozzle of the thruster. The thrust is not very strongly affected by the angle, but eventually there's a reasonable range that I think will be very possible to control in, that we can modulate. We can get a good, thrust response by opening and closing the ball valves. But this model is not quite right because it shows the flow cutting off at 85 degrees. We expect it will probably shift all of this to the side, sort of, and it will cut off sooner than that. But that's what the CFD is for, and the real-world tests, ultimately. Here's some looks at the CAD of the reaction control system. It's very difficult to take pictures, but there are 3 valves. There's the solenoid vent valve, which is here. Then there's the 2 controlling servo valves. They all run in pipes going up to the RCS wheel here. These can be replaced with braided hoses for possible easier installation, but hopefully they won't need to be because this is more compact.
Where are the pipes, the tubes made out of?
Copper. They're rated to, over the MEOP of the tank, so it should be no problem. It's the same as used in the feed system at the other end of the rocket. And that's all of the slides about reaction control system.
Is this system functional at launch?
So this is something that I noticed about the IREC rules, but it's not a thing in the far out rules. They do allow flight control systems to happen during the burn of the engine.
Go ahead.
So it will be functional at launch, unless far out says don't do that, or we decide it's too risky. It can be, I suppose.
My concern is if you have a valve that's stuck open or commanded open, either way, your propulsion is going to be venting your gas, and you're going to lose a potentially significant amount of propulsive gas here and not meet your altitude, which to me is a safety risk. That I'd rather see this rocket. First off, you've got a thruster potentially that's venting, and secondly, you're losing your propulsion efficiency. I would reconsider whether you want to keep this system active at launch, whether you want it looking at the pressures. You may need to map it that, for T plus so many seconds, this is if the pressure's below this much, the system turns off. And, once if it senses that you're no longer thrusting, then let it have fun. But I would really consider when you're going to make this system active and the potential to the flight, because you'll lose one of your propellants if it fails.
Right.
The other question I have again is testing. I guess the question would be is, I would all know, even like, do you have any kind of ground testing plans, or like maybe put it on a turntable or something?
Yep, that's exactly what we have planned. We
We
have
have
a
a small test
tank
section.
that we will just put the bulkheads onto and put it on a spinning thing and spin it around and measure how much the angular acceleration and the angle and the pressure in the tank and everything.
And again, you'll have to model inertias too. to
Yeah.
see if it works. Yeah, I mean, you really need, one of the things that's been kind of absent in a lot of the presentation here is test.
There's a testing section.
Okay. Is that overall of the vehicle, or is
Yeah.
there any subsection testing, like for testing the system?
It's everything.
Okay.
So what's driving? I'm much more basic question. What is driving the RCS requirement?
Remaining cold gas from the burn. So there's going to be some nitrous left over, which we will close the vent valves for, so that we can retain that, and we'll close the main.
Well, you're asking why are we doing this?
Oh, why?
Why?
For
Just
fun.
to maintain roll control.
For fun.
Yeah.
There's no actual requirement to maintain roll control.
This system can be shut off before launch and we can still fly.
Yeah. It is.
The reaction time that you're going to need to maintain roll control is
Yeah.
really, really tiny. And those ball valve things, have a real hard time thinking. I could see going totally unstable.
It's possible. We were considering a control method of having both valves open and then sort of just changing the level between the valves as a way to get quicker control of the thrust.
And you're losing one of your propellants.
Yeah.
The whole process.
This would be after the burn, most likely. I mean, we brought up the idea of it's able to be on at launch, but I think we'll probably have it go after the engine burnout, so that we can actually use it as an experiment.
I would feel a lot better about it
Yeah.
if the system was not active while thrusting.
I think that makes sense too.
I almost
Your
know.
potential
Yeah.
spin rate could be really high, and you're going to be trying to control the
In fact, I would call it a recommendation for the panel.
without having a really, really proven control system. I'm just
Sure.
skeptical that you're going to be able to do this
Right.
with what you described.
So we're planning to use the RCS system as a payload for the competition. It's truthful, it really isn't for any mission critical thing. It is purely because it's a good way to do experimentation as a non-mission critical requirement. So we're using this as our payload for the competition, and so it should be fun to experiment. Even if it doesn't work out so nicely, it'd still be all right for
In
us.
fact, if you could get the control system good enough to maintain roll control, then
Yeah.
you could also have pitch and yaw control.
Yeah, in theory.
On what the arrangement you have. And it should be more than enough for pitch and yaw.
Sure.
If it can control the roll.
Right.
But I'm just skeptical that you'll be able to get a control system, and valves.
Yeah.
To deal with it.
Yeah, valve selection was a big thing. So
If it's post burnout, it's less flight critical. If
Yeah.
you have a flight critical issue, if it's operating during thrusting, I would call it a recommendation from the panel.
I agree with that.
I put words in your mouth, but I would call it a recommendation.
Yeah.
Great.
Especially, trying to do it during the burn when you can put more pressure on the whole system.
Yeah. I definitely agree with that.
Unless you're
Yeah.
a really proven control system. I'd be very skeptical. I don't think I'd want to try it.
Right. All right, I agree with that. Shall we move on to cameras? Are there any more questions regarding RCS?
Are
Great.
There we go.
Yeah, get up there.
Alrighty, this is not a flight critical piece of hardware, but I got to leave in a little bit, so I bumped up. And it probably makes a little bit more sense after Noah talks about his avionics bay, but just to clear some things up regarding the camera system that's going to be on board. We're going to have a GoPro in the engine bay. There's like 4 struts that are that hold the fins that will just attach via screw the GoPro. That'll be just a non-transmitting camera, but we also have plans to do a live stream project. We're currently configuring that. We've done a few different live streams so far, but what we're going to try to do is we're going to try to implement an analog FPV system. We have it was like a $74 kit of just a basic parts. I believe it's at 5.4 gigahertz, something like that. I can't really remember. We spent a lot of time trying to configure for a digital FPV system, but right now we're going to be transitioning to an analog system just because of the range. This thing's going to go up to like 20,000 feet, so we want to have as much range with the cameras as possible. And then for the avionics bay, Noah's going to go over this all a little bit more. We have it built in the ability to configure with these different camera systems. For the analog system, this is where the batteries are going to be mounted, and it's going to be right there on this. It's like, what would you describe it? Like a swivel hinge. If we were to use a digital FPV system, which we can go over next, we have, so to get the digital video, we need to encode whatever video that we get via CSI ports. There are different Raspberry Pi cameras that we can use. Plus, we can also implement the GoPro via an HDMI CSI bridge. And there's 2 different CSI ports on this carrier board. And then we need a compute module for that, which is also by the Raspberry Pi. We're going to load up what's called an OpenHD Air Unit software. It's essentially, there's a big open source platform for digital FPV that we are thinking about using because they have reported that you can do long range. There was one that did a 20-kilometer flight, but we may not have the hardware for that. We may be just good enough for 20,000 feet. And so the reason we might want to do a digital FPV system is that when we implement that into the live streams with OBS, our broadcasting software, we can get higher image quality, up to 720p from the rocket, which would be pretty cool. And be definitely great to have for our outreach events. Next slide. Timeline. So far we've had 4 live streams. This one is one of them. We've had 2 live streams from remote locations. Both of those have been using cellular, but we have transitioned over to Starlink. When we put together our PC that we're going to be running a lot of our data off of, this goes beyond just the live stream, but just data acquisition in general will be going all to that centralized computer that we have over there. We managed to get the specifications that we needed pretty cheaply so that we had enough money left over for Starlink. And we've already done a couple tests with this. We only get about 3 to 4 seconds of lag, which is good enough because we're not actually controlling anything. At least the camera system isn't. And then the to-do list before February, we already have the hardware for the digital FPV system. We're going to be trying to work on the Wi-Fi connection between the transmitter and then the ground station. And then we also want to purchase the analog components. They're not terribly expensive, so they're going to be within our budget. And then test that range and latency with that as well. So not super flight critical, but it is interesting and cool to think about. So Any questions on cameras?
Crazy time. What time? It's 4:58.
Okay, cool. Next up, GSE.
Okay, hello, I'm Alexa again. So the GSC has already been designed, created, and has been implemented many times. We've been using it. It's based on the Sonoran Wildcat GSC, and we will be upgrading it in a way that it can be used for Jebediah and for the Sonoran Wildcat. There aren't a ton of critical upgrades for it to be compatible with the new rocket, so there's not a ton that's going to be changed specifically for use with the new rocket. Most of the upgrades are just going to be for easier use and just more convenience. So currently it controls the igniter, so the relay, the fill, and the GSE vent valves. And this is currently done with an RC controller used for planes and stuff, and a receiver connected to our GSU, which sends these signals. The GSC will monitor and report the bottle pressure upstream of the fill valve. So we do this with our pressure transducer cables that we plug into different parts, and that data is put onto our data queue and then sent over wireless Ethernet with a Raspberry Pi with a forwarded connection with our TP links. Then the GSC shall utilize a quick disconnect based on the half-cap design, which is for the tubing. And it will be controlled with wireless telemetry. Yeah, and so there's, we're going to have an upgrade, which I'll talk about later, which is our GUI. So we won't be using our RC controller anymore. And then the GSC will have a 2-hour battery life. Yeah. It's kind of crazy. Anyways, so here's a picture. This is what it most recently looks like, and that is from before. There's, it's kind of hard to see since that one's kind of zoomed out, but there's a lot less going on in here. It's not because it's the same, they function the same, there's just a lot of materials taken out because of the PCB that has been implemented, which is this. I guess we can so the PCB, which has now been implemented, as opposed to for PDR, it was not in the box yet. It eliminates the need for duplicates of a lot of our materials that we had. We originally had a lot of voltage switchers and power bars and buses, and we had 2 batteries, and we had a lot of wired connections that could be simplified. So the PCB doesn't have any intelligence on it. It's basically only forwarding connections and making it a little easier to see. And using this, we have control over how thick the wires are kind of in there, and it's a lot easier for a lot of different things to get the same power without having so many different wires going through the box. The PCB also helps prevent brownout of data acquisition electronics upon ignition. This used to happen. We had our igniters were pulling too much current and causing a brownout of our electronics, and with the Raspberry Pi, if it powers off, it takes 90 seconds for it to power and then reconnect, and by that time we've already finished our firing and there's no more data to collect anyways. So with the PCB, we're able to put more resistance in series with the relay and the igniter, which prevents so much current being drawn from the batteries. The PCB also supports use of our RC controller, which we're using right now, and it will support use of our GUI for valve and relay control, or valves and relay control, because or I guess we can go to the next one. So here's what it looks like. Here's the CAD and the, So here's where we have our from the receiver, we plug in stuff right here, or the wires right here, and this goes to where the actual the materials are. In the new design will have a Raspberry Pi, which has a program that it runs to be able to receive like commands that are forwarded to a PWM controller, and that forwards that signal here so that it can send out commands for when we need to open and close things. So it can be used both ways, and it's good for testing. So we've been able to practice using it or developing the GUI, and we can quickly set up the testing and then set up actual like the receiver we're currently using to continue testing. And then so here we have like the whole thing is we have a thing for our battery. This is connected to these switchers, which are 5 volts and 5.5 volts. So then we originally had like 5 or 6 switchers, I think, and now we're reduced to only 2, so that we have a lot. As you can see, there's 2 traces that are very thick. These go to multiple places on the board, especially these, the receiver and the valves and the relay. This is important because originally our receiver was providing power to our valves and relay, which is not a super safe thing to do since it draws current, and if we're doing multiple things at the same time, that could be an issue with something not working at the same time as another. With this, we're able to provide power from the board directly to all of these, so that it's not relying on just the receiver. We also have these two screw terminals here for our data acquisition transducer cables. They are screwed in here, and then the signal goes to here, and our data queue sits on this side of the PCB, and so we have a really short place for us to do this. Very easy to tell if something is unscrewed from the PCB or the data queue, which is something in the past that was kind of hard to tell. And we also have 2 spots for, oh my god, I'm sorry, I'm blanking, fuses, in case something goes wrong, so we can protect the board and other electronics in the box. We also have power for our Raspberry Pi, it's kind of hard to read this, and our Ethernet extender. So, and then for our igniter, we have power coming here, goes off to the igniter. We have this resistor in series. It's not exactly in the spot in the way we've used it. We've put it somewhere else, just complicated, but anyways. This resistor provides enough resistance in series when we ignite for it to not draw so much current that it browns out. Okay, next slide. For the new GUI, I explained before, so it will be created with HTML on a Raspberry Pi server. So the Raspberry Pi will create a server, and then you go on like Chrome or Safari or something, and you enter the IP address and some like whatever it is, and then it'll show up as a little like website, and then we're gonna have it so it shows like a fill valve open, and you can click it, and then it'll tell you when it's open or closed, and then we'll have like ignition relay. And part of the goal for this is to handle the relay and throttle offset, currently done manually during ignition. So right now we have to, you would think you just do both switches at the same time. The way we do it to make sure it actually ignites and goes is that we have to do the ignition first and wait like a second or 2, and then do the throttle to make sure that it goes. And with this, we could just program it to automatically do that, so we just click one button and don't have to worry about that. And as I explained before, the way it works is the Raspberry Pi and the computer or whatever we're using to connect it with are, I guess, and in the future we will do the same thing that we do with our data acquisition, is wireless Ethernet connection. So when they're on the computer and the Raspberry Pi are on the same network, the computer can start the program on the Raspberry Pi and then open the website or the server, and then the server should be able to send commands, and then the Raspberry Pi can send those commands to the PWM controller, and then that can give the commands to our relay and valves. Any questions?
Yeah, where are you on this? We've got a lot of
sorry, I guess
a lot of bullets that say will be and will, this, and when do you need it?
So none of this is critical for the new rocket. This isn't like has to be done. This is more convenience and just developing our like skills with electronics and so there's no deadline technically for it. I think we would like to have it ready before the launch in January so that we can.
So
use
what
it.
are you doing now then?
We're working on programming the GUI. We have
I mean, what is critical for the launch, and what's the status of whatever that is?
The GSE works for the Sonora Wildcat. The only change we'll need to make for the new rocket is adding like valves to connect to, because we'll need multiple bottles. So we won't actually need to change much with it. It's going to be the same controls, same data acquisition, like same setup. We'll just need to add like some extra tubing for the extra nitrous bottles.
Okay, well, and when is that needed? I'm getting a little concerned about just the schedule here, and I apologize. I don't understand a lot of this. It's just just coming at it from a program, program standpoint, and because this is. You are talking about things that you do need, and I'm not hearing when they will be done. And this whole new board, if you're saying it's not being needed, then it becomes a matter of resources, of putting your resources where they are needed versus where they aren't needed. And I don't have an answer for you. I don't even have a recommendation. I have nothing. Other than it's not coming across to me like this is crisp, if that makes sense.
Well, yeah, in terms
schedule.
of what needs to be changed is just valves or just tubing to the nitrous bottles, and that won't be necessary until we're ready for static fire, which is, we haven't built anything yet, so there is not really not urgent need to fix or get things ready for a test that is not going to happen for many months. So we'll look into that once we start making progress on the rocket, like getting more tubing, because we also haven't actually figured out what kind of bottles we're using, what we're going to do. So we're kind of waiting on finalizing that, and then once we get closer to a test, especially because we're not sure about our funds entirely.
Okay, so what I hear you saying is that the system exists now, which needs to be modified for your configuration.
Yeah.
Sounds like you're not concerned about the extent of those modifications.
Based on the design of the new rocket, it's designed kind of to be compatible with this, or like there's very, very minimal changes needed. There's only changes we want to make our system nicer and easier to use.
Yeah, I'm just going to jump in to clarify. Genuinely, the only difference as it is currently is that we have more nitrous oxide. So all we're changing is adding, I think, 2 extra bottles of nitrous in parallel with each other. Everything else, as far as the ground support is concerned, is the exact same. Same valve, same PID, same data acquisition. We're literally just adding a Y connector for some bottles.
And so the PCB that you described is something new, or
it exists and it has been tested.
Yeah, it's already a part of the system.
Yep. We've done some static fires of the prior rocket on that design.
Okay.
So
the interface that you were talking about.
That's what's in progress.
That's what's in progress, and there's no specific deadline because it's not critical for any thing we do.
Yeah.
Just to add to scheduling, because that's also been a concern I've been thinking about a lot recently. This week we actually had a budget scare. We didn't know if we were going to get all the money that we wanted. That just got sorted out today, actually. So a lot of what's going to happen next is, coming back together and reorganizing our thoughts of how we're going to properly schedule the next semester.
Yeah, especially since GSC is changes are non-critical. We don't need to buy anything since GSC has taken a kind of a backseat on asking for funding and new materials since it's not necessary right now. And since we weren't sure about our funding, it was kind of, we were just kind of staying as we were.
Speaking from experience, GSE will kill you. When we go to handle missiles, launch missiles, whatever, If the GSE isn't working, you're not launching, you're not flying.
Yeah.
So don't belittle your importance of the GSE to the team.
Yeah.
And it makes me nervous anytime someone says, "Oh, this will be easy." That makes me nervous. When I hear that, my response would be, "Okay, then do it now. If it's easy, do it now. Get it out of the way. Test it." Rather than saying, "Oh, it's easy. I'm going to put it off."
Yeah.
Sure.
I'd
I
rather
think,
see the opposite.
like,
of
it's
someone
literally
saying,
we'll just get more braided hoses. and
Okay, then go
screw
do it.
That's
Yeah,
it.
go
Yeah.
do it and get it off your plate. And if it's that easy, because
Yeah.
I agree, invariably something will jump up at you.
Mhm.
You still worried me, it's just as simple as adding nitrous, but you have deficiencies in the existing system that need to be corrected, like the brownouts.
Well, that has been corrected.
Okay.
There's no issues right now.
Okay. As far as integration, you have the smaller rocket. Again, if the interfaces are basically the same, you can use that as a hot bench for testing your GSE. I said, don't shortchange the GSE, because if you don't have a GSE, you don't have a flight.
Yeah. That's why we do a ton of testing all the time to make sure all of our controls.
Okay.
We have had static fire 11 with the Sonoran Wildcat. We've been iterating on the GSC. I was in charge of it last year.
Okay.
But in the current stage, there's been little to, if not no, change for, like 3 or 4 static fires now?
Yeah.
And anytime we did have an issue, it hasn't been with GSC. It's proven to be pretty good so far. We'll continue testing.
The other thing is, I keep hearing about resources like money. I'm not sure if you've got enough people for the work, but you need to prioritize resources. What's absolutely essential for your requirements? What is nice to have? Now, as we talked about the RCS earlier, that's a nice to have. So if it's going to take more money and time and people, that may become a lower priority versus, say, GSE or some other aspects of the airframe. Same thing with the cameras. Yeah, it's nice to have the live stream and everything on there, but again, is it a priority for your mission? And again, all of your resources, time and money and people. You need to balance everything to support that.
Any other questions?
Yes, thrust structure. So this is about mostly just the system of connecting the engine to the rest of the rocket, and I guess the more general structure of it all. So, the requirements, it must have rail guides that work with the rails that have it far. The engine connected with angle brackets and a double connection is apparently a very reliable way that lots of schools use, and it's recommended by Half-Cat Rocketry, and that'll make a lot more sense on the next slide. We want to be able to cover the engine section for aerodynamics. This was not a feature of the last rocket because of how it was designed, but, well, it sort of was, but we're going to make it a lot more of a priority, I suppose. We must be able to disassemble the propulsion system, so this is what disconnects from the tank to help make the tank be 8 feet long for transport. And we must be able to mount this to an I-beam for static testing. So this is what we have. It's just a scaled up version of the Sonoran Wildcat, where there's 4 L brackets they have 2 bolts connecting them to the tank bulkhead here, and they have 2 bolts connecting them to the engine. They also have the fins bolted onto them because they were in a convenient spot for that. And they go over a 6-inch fiberglass tube that makes it all a little more streamlined. You can see these bolts they go through several layers. They go through the L bracket, fiberglass, the engine spacer, the chamber wall, and then the nozzle retention. And then a similar deal up here into the injector. It covers up the valve area, as you can see there.
All right, stupid question time. So just looking at this, the ring that retains the nozzle,
Yeah.
it doesn't look like from this picture that you can put it in there.
This was actually a thing we realized a couple of days ago. This is able to be put in. The version that was in some previous slides was not. It does fit around the bell of the nozzle, but it is sort of tight. But it's
the exit diameter is smaller than it's shown here.
no, it's just probably the angle that the outer exit diameter here is smaller than the inner diameter of the retention.
Okay, so that figure does not look accurate.
Yeah, it might be a little weird looking.
Good note to check that though, just in case. It really can't hurt.
Mhm. That's actually it for the thrust structure. That's it was just the question slide now. Any other questions?
Well, that structure is what I've done any structural analysis. Just thinking it's over designed. Bending loads through there. It looks like those 4 L brackets take all the bending loads. Is that true or?
Yeah, they take all of the loads going through that area, not just because that's really the only thing. This fiberglass might take some loads, I suppose, but I'm not counting on it.
Is that four beams like that, I would think that the resistance to twisting would not be very high.
Well, yeah, I tried to do some buckling analysis on these, but the results were not very good, I guess. They suggested something unrealistically high for when they would buckle, so maybe they are over-designed. But the torsion, I mean, hopefully not too much torsion will develop, just because it's only the engine down here.
Even if those fins are going to be potentially putting torsion on.
Well, yeah, I guess the fins are responsible for that. But
Because that's not a pressure, so that there's nothing structural other than these 4 L brackets that goes between the engine and that forward structure.
yeah,
Are there any bolts going into the fiberglass, or is it just basically sitting there and it's not a structural element?
well, so the fiberglass is among all of this, and the bolts do go through it, so in some ways it could provide structural assistance.
That could. I mean, that's what the skin of an aircraft does. It provides the torsion.
Yeah.
So it could do that. Whether you designed it to do that or not. Whether inherently the fiberglass would do that. I don't know. I'd like to see a little more detailed thoughts on this one. That structure, having just those 4. So without the fiberglass, that just looks kind of sketchy to me. Whether that would work or not.
This is the same way that's used on the Sonoran Wildcat.
Same length, but it seems kind of long.
They are, well,
Longer.
it's scaled up just because the rocket is bigger.
Okay, but that just means it's longer. Now you got a bigger motor.
Yeah. It could maybe made shorter at the cost of a more crowded area here.
But it's not a bad solution if you were to say, I'm gonna use that fiberglass tube to provide my structural torsion. And that, skin like that provides both bending and torsional resistance. So it wouldn't necessarily be a bad thing.
Okay.
Fiberglass is pretty good.
Yeah.
I'd get somebody who really, this is it's somewhat of a complex structure. You really ought to have somebody who's looked at complex structures like this. Not me. I'm just.
Actually, the reality of it is, I'm not sure how complex, basically your longitudinal elements are the 3 L brackets, or the 4 L beams there. I'm looking at it, I'd almost suggest, as a potential, is to put a L bracket on the opposite side, so you have kind of a T section, effectively.
Oh.
You're saying adding 4 L brackets?
Add 4 L brackets, so they on each side, you could put them on each side of the fin, sandwich the fin, or, that's probably what I would do, is just sandwich it.
Yeah, we actually have the L brackets in downstairs. If we want to go look at them after the presentation, because they're pretty hefty, but then again, it is a big rocket.
Yeah. It's a long rocket too, and
Yeah.
which brings up one thing I've never seen presented anywhere here, or I missed it, is do you show anywhere where the CP and C is on this rocket? And
That's coming up, I think. No?
That didn't make it in the presentation. It was supposed to, but we didn't cover that.
And and the other part that relates to that for stability is what's the CG shift going to be as it goes through flight?
Yeah, this is a interesting topic because I gather it would be totally unlike how a solid motor burns.
Right.
Just because all the fluid drains, and unlike how the Sonoran Wildcat burns, because the CG just goes straight down as the fluid burns, and then it goes back up once it's all out of fluid.
You really, because FAR is going to ask for that. Anyone who just wants to know what's the basic stability of this rocket, what's the CP and CG relationships?
Yeah.
How would it come back up?
When the mass of the fluid gets outweighed by the mass of everything else ahead of it.
But it would probably move only slightly considering the mass of the propulsion and engine at the back. Depends on the payload, but.
I'm not sure what the plan is, whether there's another follow-up CDR or whether there's a launch readiness review or something, but somewhere in the presentations, either now or in the future, that has to be included.
Mm-hmm. All right. On to recovery.
Cool. Alright, so there are some requirements for recovery imposed on us from the competition. The main ones are the descent rates under drogue being between 50 and 150 feet per second, and slower than 30 feet per second under main, deploying at an altitude between a third of our target altitude and above 1,000 feet. The other requirements are just imposed that we use a 2-phase recovery and that we have a fiberglass airframe, and that this experimental airframe that we're making has to be tested for its material and failure properties. Some other requirements are to have some extensions on the coupler joints. The separable joints have to be extended at least 1.1 caliber, but we are going to design it to be 1.5 cals. Inseparable joints are a minimum of half a cal, but we're also going to design them to be 1. The safety factor of all of our hardware is going to be designed to be 2 times the calculated snatch force, which is the maximum force experienced when the main chute opens at drogue velocity. And these other requirements are that we need a swivel and that shock cords have to be rated to withstand more than our safety factor of the snatch force. Comparison to the Sonoran Wildcat is they're roughly the same. The descent rates are within the requirements of the competition. being between 50 and 150 for drogue, and below 30 for the main descent rate. The main diameter is smaller, but it is a more efficient parachute, and that allows us to minimize our snatch force and maximize our descent rate and kind of balance the two.
The rocket weighs, what's the empty weight on the rocket, which is what it will weigh during recovery?
Around 95 to 100 pounds.
Okay.
All right, the first thing we started doing was creating our own experimental composite airframes. Now, this will be a fiberglass airframe made of 10-ounce 12-week fiberglass with a West Systems epoxy matrix. These are handmade on drawn-over steel mandrels. There's a picture of it there. We have long 5-foot sections that will compose the entire forward section of the rocket. Previously, we've been making these tubes with a Teflon and lubricant mold release, but to try to reduce costs, we're going to switch to polyethylene sheets to help make it not stick to the steel.
Good.
And here's some pictures of some of these experimental airframes being made. They've yet to be tested for all their strengths, but we will hopefully soon be working with the materials science department to work with some of the machines to figure out what these properties are.
Do you have any threshold numbers that you have to meet by your design?
The competition doesn't have any threshold numbers.
But does your design have any threshold numbers that you're looking for if you're going to go test it?
Probably just to withstand the launch force. Make sure it doesn't buckle under load, under the launch loads. But these airframes were made on the third recovery flight vehicle, and they came down no problem with no damages. The nose cone will be made the same way with the experimental layup method. We are using a Von Karman 5:1 ratio nose cone with a 6061 aluminum nose tip connected to our end bulkhead, which is made of G10 fiberglass, through a 3/8-24 threaded rod connected with washers and lock nuts at the very end of the bulkhead. The load rating for all of our recovery parts have to be a minimum of 12,750 pounds. This is twice the theoretical maximum snatch force that we experience. And as such, we chose parts that were rated to be well over this 2 times factor of safety load. All these parts are rated to a minimum of 3,000 pounds, with the shock cord being rated to closer to 6,000. Likewise, our experimental G10 fiberglass bulkheads were calculated to also withstand the minimum rating, with a safety margin of 2 when we incorporated calculations using the 3/8-24 hardware with 1-inch outer diameter washers. We used experimental numbers from theoretical numbers of 19,000 psi for its tensile strength, which was just average numbers that we found from resources online. We found that it would roughly survive 6,000 pounds of continuous load.
How thick are the bulkheads?
1/4 inch. Our deployment altimeters are these 3 boards here. So we have an Altus Metrum Telemetrum, which will run off of a 900 milliamp 1S LiPo battery, and it can theoretically last up to 9 hours. The max operable altitude for its barometer measuring device is around 100,000 feet. The second altimeter board that we'll be using is the Blue Raven, which is a requirement by our competition. This can run off of a 400 milliamp LiPo battery, and there isn't really a theoretical value that we have to find, so we have to conduct battery tests to see how long it will last. The max altitude that it can operate at is around 45,000 feet, and the last board that we'll be using is a featherweight GPS tracker, which runs off of the same battery as the Blue Raven and can last up to 16 hours off of its data sheet.
I mean, the same type of battery, not they're independent batteries.
Yeah, all 3 are independent batteries. And the battery lifetimes of these 2 featherweight boards can be increased if we use the same type of 900 milliamp battery.
Just to make sure FAR has no limitations on LiPo batteries?
None from the regulations.
Okay.
So this is our recovery sled. This will hold all of our batteries and avionic equipment. It's designed to fit within the experimental coupling tube of a fiberglass airframe, which is rated to be which is designed to be 5 inches and 3/4 of the inner diameter. It's designed so we can easily test all the boards and power them on without any trouble. And it's also designed to leave room to expand and hold all the camera systems that we still have to put into the rocket. They will be held within the AF bay with the same 3/8-24 threaded rods, which were found to be having a tensile strength of 150,000 psi for McMaster, and they were calculated theoretically failed around 13,000 pounds of force per rod. So these are individual close screenshots of the sled. All of the boards will be powered individually. They will all be separate circuits powered by 3 different screw switches. All of the boards will use LiPo batteries, and they'll be held in this battery compartment. And all the boards will be mounted directly onto the main sled that will be attached directly onto the threaded rods. So how the rocket will separate is with black powder explosive charges. All the coupling joints will utilize 4 number 4 nylon screws as their shear pins, and the size of the charge will be determined through ground testing and just through basic calculations. There were some concerns over the combustion efficiency of black powder at elevated altitudes, roughly between above 15,000 feet. But some sources say that that's not too much of a concern as long as the space between the particles of the black powder are minimized, and we can do this through wadding within our charge pump.
Also, the integrity. One of the ways I build the charges is to use some half-inch diameter paper tubing and seal both ends with epoxy, so it gives more compression. 15,000, I think the number I've seen is typically above 30,000 feet AGL, but you can't go wrong, again, making sure that the charge wells are sealed. We can talk about, a higher compression design for it, because I'm sure I'm going to be the testing ground for your
Oh yeah, definitely.
for your charges.
All right. Any questions?
Not for you, but going back to some of the on the previous subject, didn't ask the questions. What's the max velocity of this rocket?
Supersonic.
I
don't know.
Barely supersonic, or are we talking significantly into significantly supersonic?
It's like slightly above Mach 1.
Well, if I really wish we did finish an open rocket. I expect it probably will stay below Mach 2, but well above Mach 1.
You're well above Mach 1. Okay. So that's something probably we need to know is what is the max velocity that you intend to see.
Yeah.
And then that leads to the other question going back to the structures is have you looked at flutter on your fins and how you're set up there?
Their Far Out actually has a specific flutter calculator that we use.
Have you done that then?
That's something we were going to do tonight.
Okay, you need to do that because again that feeds back into the earlier questions about the frame rails, because again the flutter may be that those L brackets are contributing too, they're not stiff enough. So yeah, those are critical elements that need to be done.
Yeah.
You're using shear pins?
Yes.
Okay, you haven't figured out, I assume you haven't figured out how many shear pins or anything yet, or?
No, not yet.
Okay.
We're estimating 4.
Okay. And it's going to be fiberglass tubing holding everything. What's the one thing that would be helpful is to have an inboard profile. What's the layout of the chutes? Is it the classic main Vendrove, or are you doing something different?
It should be the same as we've done previously.
Okay. The other thing is, like to see sometime in the future too, is what's the length of your recovery harnesses, so we see what's going to bang into everything else.
Yeah. Usually we have it to where it's 3 times the length of the rocket, but because it's estimated to be
66 feet.
yeah, 60 feet is kind of outrageous.
Okay.
So the largest we found was 40 feet, 40-foot shock cords.
Okay.
So I think we're just going to run with those.
Okay. I would like to see the the different lanes just so we can see how things lay out when it's coming down.
Mhm.
That's all I have.
Okay. Testing. This is basically just like what Far Out requires us to test. It has the April 15th deadline for all tests needed for competition. They must be safe, of course. They must collect all the data that they're supposed to collect. And the goal is that we must complete 2 static fires. But we can't do static fire in flight configuration because that would probably cause a lot of damage. So we'll have the tank vertical and the engine horizontal.
You said 2 different things there. Is it a requirement or is it not? Like, shall complete 2 static.
Yeah, it's a requirement.
So it's a goal.
Yeah.
What's preventing you from firing statically vertically?
The I-beam is probably not tall enough. We wouldn't have very much clearance between the engine and the ground, and we don't have a flame trench or anything. So
Which we'll show the I-beam in just a bit as well.
yeah, there's a picture of it.
I don't suppose Norm can get out there with a backhoe and make a flame trench.
Yeah, he could actually.
Maybe he could. But it also does seem like it's rock right underneath the I-beam.
It was.
It's
But
pretty
he drilled a
granite,
hole
right?
in it, so I don't know. Maybe it's fine. Anyways, here's some of the tests we're going to do. Pressure-proof tests of all of the pressure vessels. We filled with water and we pressurized them to 1.5 times the MEOP. We do water because it's incompressible and it won't explode in a failure. Injector flow test. We need to flow water through the injector manifold and try to measure the discharge coefficient to help model the engine accurately. Static fire, that's, we mount the entire propulsion system together, fire the engine horizontally like we were talking about, and prove that the whole system will work together and that we can get accurate models for flight.
The FAR doesn't require the specific configuration in your static test?
Nope.
It's propulsion system only.
Yeah. It requires, actually I don't know if it requires, the plumbing diagram would be identical. It's just the flight, the actual physical manifestation would be different.
If you can do,
tubes, that would argue for your tubes being braided.
Yeah, sure.
Yeah.
I think that's probably what we'll end up doing. It just hadn't been updated in the model.
if you can test vertically, I would strongly, the old saying is test like you fly.
Yep.
And because you're going to be enclosing the compartment, I don't know what kind of thermal environment you're going to have in there. So I would make the biggest effort to test the propulsion system all up vertically.
Okay. Well, the next test we're talking about, the RCS spin test. We talked about this before, where we have a small tank, and then we put the bulkheads on it with the RCS and we spin it back and forth. Try to tune the control system, and then of course take out the inertia and change it back for how it would be on the real rocket in the model. We have range tests of all of our different remote controlled electronics. That applies to the GSE, the rectangle, and the recovery systems. The rectangle should probably be test flown on a smaller solid rocket, just transmitting and recording data, not connected to anything.
You're saying it should be.
Well, it would.
Not currently.
It's not currently a requirement, but I think it probably should be a requirement. I think it will get done. Parachute ejection test. This is, a standard for almost all rockets, amateur rockets, where we fire the black powder charges on the ground, ensure that the rocket separates and the parachutes exit their holding bays, and then a recovery test flight where we fly the recovery system on a solid rocket motor, probably at a somewhat lower altitude, but just to make sure that they will deploy as expected in a flight environment.
Again, the best you're going to get locally is about 13,000, actually about 12,000 feet.
Yeah, we'll be going too far.
Oh.
Just because we want to use a sugar motor.
Okay.
Because
We know a guy. Rick, is it Rick Loader?
Rick Mashak.
Rick Mashak, who's able to.
The motors to simulate this rocket would be way, way too expensive.
Right.
Here's some pictures of some of our testing. These are both at FAR on the I-beam there, which is much smaller than the I-beam we have. This is showing the data collection we had. We got this data live, and that's just a cool camera angle of the static fire there. This is about our new I-beam. So as you can tell, this is a very tall I-beam. This was 20 feet tall before we put it in the ground. Now 14 feet of it sticks above the ground. There's a operator driving this forklift. And that's the hole I want to do. And then this is the new I-beam put to use. This is Sonoran Wildcat firing on it exactly 1 month ago. And this is, that gives a sense of scale and how tall it is. But even with being 14 feet tall, the propulsion segment of Jebediah is 11 feet tall. So if we were to mount it at the very top, which we'd have to remove that pad eye there, we'd only have 3 feet above the ground, which would kick up way, way too much dust, possibly back up into the engine. We could maybe mount it way higher, but at that point you need a cherry picker or something. And that's all we have about testing.
So what I see the testing program being very weak on is I don't see any integration testing, development testing on the rectangle, basically the integration of any improvements on the GSE to the rocket. So you need a lot of development testing. Most of your testing here is on the airframe and full up. There's very little testing of your electronics. Also, with all the electronic systems you have on this rocket, you need to do a test with everything powered up to make sure that they're electromagnetically, they're not interfering with each other, because you've got the servos generate noise depending on how it feeds back into systems.
Yeah.
So I would say that's probably one of the weaker elements here is the testing, because I don't see a lot of lead-up testing to the all-up round testing.
Thank you.
Yeah, there's definitely a lot more tests we will be doing, but
going back though, your schedule needs to reflect those, because again, we talk about like the rec is you don't have until say April to start doing your testing on rec. You need to have the parts probably after the first of the year to start breadboarding and get your initial rec testing done.
Yeah.
mm-hmm.
And again, it goes back to the other comment. There's a lot of testing. You need to prioritize. If, in fact, you don't have the assets, again, time, people, and money, then you need to make some hard decisions. What you can live without on this rocket, and what you absolutely have to do on this rocket.
Yeah, it sounds good. Well, the plan was after CDR to immediately order machining and all other components. So with that in mind about the breadboarding prototyping, we'll add that to, and among other testing that we have the notes of, we'll add a bunch to there. We'll have to reconvene about what exactly it is that we're prioritizing, as you say.
To be honest with you, I'm less worried about the rocket, the propulsion system, than I'm more worried about all the electronics and the overall airframe.
Yeah, makes sense. Well, yeah. Well, we'll make sure to flesh that out a lot more
Now, is there another review plan? Is there a CDR2 or a launch readiness review plan? What is the discipline? Is this something you called the CDR, or is this a requirement from the school?
This is what we call.
No, we made this up ourselves.
There was no competition requirement or school requirement.
There are the competition progress reports,
Right.
which this coincides with the first progress report.
When is the second progress report?
February or March, I think.
Yeah.
I would strongly suggest planning a CDR2. I'd be willing to participate again if you don't kick me out.
No, we won't. We appreciate all the feedback.
And I would strongly recommend a Delta CDR or CDR2, whatever you want to call it, to see, as the design's matured and you've done more testing, what the plan is.
Okay. I like
Yeah.
that plan.
I also like the idea of an integration review or a flight readiness review.
Absolutely.
Oh,
Yeah, and you can call on me. I'm around enough with the
Yeah.
other stuff, the IREC and stuff. You know where to find me.
Awesome. Well, I'm sure we'll keep you up to date as well as we continue. We're happy to have you with us as good resources for rocketry, so it's great. Feedback is good so far. But
Anything
is
else?
there anything else before we begin conclusion and further discussion? Okay.
Alright, perfect. So this is just a list of all of our supporters that have been helping us out throughout everything. This is Norm's company. This is where we set up the I-beam, and he gave us a lot more than we could have ever asked for. Really saved a lot on budget.
Huge help, huge sponsor. We appreciate it.
Majority, actually, I'm just going to say all of our budget mainly comes from the College of Engineering. The dean's funding and also the college funding is what kind of pushes us through everything. For this year, we had a budget of I think $22,000,
which includes all travel and other operational expenses. So for the rocket itself,
Yeah. So for the rocket, we have a budget for Jeb, $11,000. We're hoping that we can increase that through donations throughout the semester. We actually have a fundraiser this week at Chipotle, the one on University, on December 4th, if you want to
Crazy.
join. Sorry for those plug-in, but I have to.
Yeah, no.
This is the company that just sponsored us, Boltline. They really help with organization. I'd really like to show you guys the program that they gave us because it's really cool and a really neat way of organizing the club. R3 Aerospace, we were very involved with them last year. That's originally where we tested the rocket, and Rick Lord just is a great guy. Half-Cat Rocketry, that's what the Snoring Wildcat is based off of. They made this Mojave Sphinx, and all of our knowledge mainly comes from their book and what we call the Bible. And Nobel, they helped us with making our test stand for last year, and we're hoping we could get in contact with them again.
Well, they're still around.
Well, they're still around, just not as
James is
involved
busy,
as
though.
They haven't been as involved as last year.
So our main three contributors have been Norm, Boltline, and the College of Engineering itself.
The majority of the
Fantastic.
sponsors are services based. The only direct financial one so far has been this, and maybe was it Northrop technically, or did that ever?
Oh yeah, I wonder what happened to that.
Anyway, there's
Whatever.
It's a story for others.
Yes.
These are just some resources, but these are all in the supplemental, so that doesn't matter. We have one final question slide
And we'll be
in
around
case there's
after.
anything we haven't covered, but
will-
we can just talk about it after.
And we can show you the workspace as well, where we have some components that already, like some of the metal bits and pieces.
So the question I always ask, especially for flight review, is what keeps you awake at night? Other than everything.
Scheduling.
Yeah,
For
yeah,
me,
me
it's
too.
scheduling. Especially recently, the College of Engineering got confused whether if they were going to give us $5,000 or not.
Yes.
So we had to remind them, and they just approved it today, which was terrifying.
Yeah. This was a very recent thing. They confused us with our sister, very similar club, AIAA, and somehow, despite, long story short, they kind of, for a brief moment, said, "Oops, we accidentally misplaced your 5,000, etc." Which, for a rocket is very significant. So, very happy that got sorted out right before CDR.
Yeah. Another concern I have, I know recently we just said that we were going to order all the machining over winter break.
Right.
However,
With this in
the
mind.
College of Engineering shuts down the P card purchases, well, today. So we kind of have to wait until January. So it's
Well,
gonna
we
be-
can still do the machining, we just can't order more parts.
Yes, we can't.
So
order
we already
parts.
bought all the machine stock we will need.
So that was a concern for me.
But everything we order from McMaster will come the next day anyway.
One other suggestion, because I know there was a concern about fitting the nozzle and putting stuff together. Have you considered doing any 3D modeling, just printing some stuff and basically doing a mock-up
Yeah.
of your motor 3D printed?
That's a
Yeah,
good idea.
did consider it, didn't act on it though, but I think we should.
What'd you say the diameter of basically the airframe is?
6 inches.
The engine itself is a 5-inch, but the overall airframe is 6-inch diameter.
So the overall length of the vehicle is
20 feet.
20 feet?
Yes.
Yes.
Is that HP 35 on
No, 41C.
the? Okay.
HP 35.
You said 6 inches?
Yes.
So 40 to 1 over D.
Yeah.
Pretty long.
Yeah, bending.
Holy rockets. True Jebediah fashion.
Don't say that.
It's
It's,
Yeah.
You probably need an inboard profile of the entire rocket there. It just shows the basic layout of,
Yeah.
you know, drogue, main, eBay. I think I missed it there.
Wow, there's so many slides.
It was like 123, I think, but we got through them all. Thank you all for staying.
Okay, that's not the inboard profile. What I'm
No.
saying is to show actually, you know,
Yeah.
basically what
Cross-section.
open rocket gives you.
Yeah.
Oh, that's cool.
Just so, you know, again, you know, where the parachutes are, where the eBay is,
Right.
where's the rec tangle gonna live.
Sure. Yeah, well, I mean,
Yeah,
yeah, we'll
all
get-
of that stuff.
Yeah, yeah. Okay.
3.5 Jeffs.
Yes.
It's actually closer to 3.7 jobs.
Oh, okay. Jeff told me he was 5'8", not 5'7".
Oh.
Right.
Sure.
Yeah.
Is there any final concerns while we're all still together up here before we break off, go to the lab, further discussion?
Anyone want to review any of these slides we're going on?
I'm good.
All right.
Oh, I exited the
I
slideshow.
will go back.
Did it so
All
All
well.
right, yeah, turn on the lights.
All right. 5, 4, 3, 2, 1. Lights.
I'm gonna probably pass on the layout because I'm in there enough, but if you guys need me to come over for either an hour or for a search or something, no, I can do my normal Monday and Thursday.
All right, yo,
Yeah,
we out here. We just got done with our critical design review. We're signing off. Goodbye, Rec. Everyone say goodbye to the live stream.
Bye to the live stream.
No, okay. Well, thank you. All right, bye, live stream. Later. We will see you all.
This is the IREC.
Yes.
For